Okay, we're going to start on an introduction to three-phase systems. It's a little picture here of a generating station here and what that might look like. So before we move on to three-phase, let's have a quick look at single-phase. All right, so inside of a generator, we have coils of wire, essentially, and in the case of a single-phase generator, we have one coil of wire. So and you'll see either end of that coil of wire is line 1 and line 2. Um, so what would happen in a generator, just to review back from previous years, is that we would have a magnetic field that would pass by that coil of wire and it will induce a voltage on that coil. So in this case, we have just one coil in our generator. And so when a magnetic field passes by that coil, it induces 240 volt between line 1 and line 2. And if we have a generator that produces 122 40 volt, we'll see that we have a center tap here, right here. And that's the point that gets grounded, and that's what forms our neutral. So now we can serve 120 volt loads as well as two 40 volt loads between line and 2. So just a little less than 3 wire here, and what it would look like coming off the secondary of a transformer or a generator. Okay, so both can be applied. So the concept here is that we basically just have one coil, and in the middle of that coil is a center tap. So one phase, that's it, just one with a center tap in the middle, and that's how we make the Edison 3 wire. When we go, it's one phase, single phase. So let's have a look now at a three-phase generator. So it's the same concept as we have in single phase. Okay, so it's identical concept, but now we no longer have just one coil. We have three coils. And in this case, in this diagram here, we've just used a simple generator with a magnetic field on the outside. So north pole and a south pole. And if we look closely, we see that we've got three coils. We call that one A, okay? The next one is B, and then the next one is C. So on each coil, there's going to be two wires popping out, and so there'll be one end of the wire, and the other one's the other end of the wire. That's simple. In a case like this is a very simplified generator. If we did have a generator like this, those two ends of those wires would come out along the shaft, and they'd come out on something called slip rings. So we'd have a total of 6 slip rings here and carbon brushes riding on that to get this three-phase out. It's not too often that we have generators built like this. Just a very simplistic view so that we can see what's happening. Right, so if we look at our magnetic field here, we see that we've got a magnetic field going north to south, okay? And then we've got our three coils of wire in the middle, and it's rotating in the counterclockwise direction. So you can see these little arrows here rotating our three coils in the counterclockwise direction. Now back to these three coils, physically, mechanically, in this simple two-pole generator, they are 120 mechanical degrees apart from each other. So if I look at these windings, oops, erase all ink on the slide, pen, there's A winding, okay, A, pen, thank you, pen, there's A winding, and 120 mechanical degrees later is B winding, and then 120 mechanical degrees physically is C winding, and then after the C winding, another 120 degrees is A winding. All right. And now with this generator, I put the prime mover on, whatever it may be, and it's going to rotate this generator. And you see that these three windings are going to rotate in the counterclockwise direction. So if we take an oscilloscope and we put that one on each one of these phases and we were to graph it out, right now in the position that A winding is, okay, it is perpendicular to the flux lines. Right now in the position that this is drawn. It's not cutting any flux lines. It's going the same direction as the flux lines. And so we're generating 0 volts at this point in time right now, okay, on A winding. But as it rotates and it goes near the North Pole, we'd see that it would start generating higher and higher voltage until it reaches its peak voltage, okay? And then as it goes past the magnetic flux lines, it starts cutting them at a less and less rate until it's in this position over here. And so we're back not cutting lines. So we're at 0 volts. As A would rotate, the one end of the winding would go past the south pole. We're going to hit higher and higher flux density until we're cutting them. We're right perpendicular with those flux lines, cutting them at the maximum rate, and we generate our maximum negative voltage. Well, the same process happens with all 3 windings. So compared to single phase, there's only 1 winding. Here we have 3. Now, in B phase, same thing happens. When it goes past the north pole, it generates its maximum voltage in one direction. When it goes past the south pole, it generates its maximum voltage in the other direction. And same thing with C phase. We go past the south pole right here, let's say, generating maximum negative, and past the north pole, we generate its maximum positive. So if we were to graph these all out on the same timeline, so that's what this is, same timeline, okay, we would see that these 3 voltages are going to peak at different times. So if we look at peak here, and then 120 in this case, electrical degrees later, so it coincides with the mechanical degrees, we would see that B phase would peak, and then 120 degrees later, C phase will peak. And so if we lay those on top of each other, we can see the 3 voltages laying on top of each other, A, B, and C. And we see that they generate 3 voltages 120 degrees apart. So when the 3 windings interact with the magnetic field, 3 separate voltages are produced, and those voltages are 120 electrical degrees apart. Each voltage reaches its 0 and its maximum value 120 degrees apart from the other 2 voltages. Okay, so an example of a generator with a magnetic field rotating within 3 coils. So this is more likely the scenario. So we would have the windings itself that are getting the voltage induced on them in the stator or in the housing. And then we'd have a magnetic field on the inside rotating. And you can see that the magnetic field would be rotating in the clockwise direction here. So it would first induce a voltage across A phase. Let's just follow the north pole as it goes by. Then it would induce onto B phase, and then followed by C phase, and then back to A phase. So this is more likely the scenario when we're talking about 3-phase generators. What would happen? We'd be supplying, this would actually be a coil on the inside, okay, and we'd be energizing that coil with a DC voltage and controlling the current flow through that DC electromagnet, which we are rotating on the inside. So this is so we could put larger gauge wire in there, and in the stator, not rotating heavy copper wires, or instead we're going to rotate the magnetic field on the inside. So what are the factors that affect this amount of induced voltage? Well, so this is a bit of a review from second period. It says the length of the conductor in the generator, so basically the number of turns, okay, and the other 2 factors that affect the magnitude of the 3-phase voltage are the speed that we rotate it and the flux density, okay, is the other one. So the other 2 factors. Now, if we talk about speed, yes, we're going to generate a higher voltage, but when we do that, if we increase the speed, we generate a higher voltage, but we'll also change the frequency. And in North America here, we're at 60 hertz, and we got to maintain that 60 hertz for our equipment to work properly. So changing the speed really is an effective means to control the voltage output, because that will affect our frequency. So what we'd have to do is change the flux density. Now in this one, we just kind of got a crude picture with a permanent magnet. Okay, in reality, this is a coil, so that we can adjust the voltage to that coil, make more current go through, increase the flux density output on that electromagnet in the middle, or we can decrease it as needed. So if the voltage is too high, we can drop down the voltage across that electromagnetic, or the exciting field we would call it, whatever the excitation current is. So we'd adjust the current through the magnet and electromagnet, and then we could adjust the output voltage of our generator. But it's still, when we're looking at the stator winds, we're talking about 3-phase, it's still the same concept. Each winding is mechanically 120 degrees apart on this simple generator. So what do we do with those stator windings? Okay, so the ones that we're inducing the voltage on, what do we do with these? Well, there is a couple of methods, or a couple of different connections we can do with this 3-phase output voltage. And so in that generator, I can connect them up end to end So end to end, and then the next one starts, and then the next one starts, end to end. And on the corners here, I can bring 3 lines out to my load. Okay. So if you notice here, there's no ground on this system whatsoever. There is no neutral. So this is called the delta connection. All right. So our 3-phase, 3-wire system, and it is usually an ungrounded system. So that's one of our connections, the delta connection for this generator. We can connect up loads to this in Y or in delta, but this generator itself is a delta connection or secondary of a transformer. It's a very similar principle. So we're talking about these end of the windings. You're going to see me using this term, little a, or big A, little a, big B, big C, and little c. And that's a way basically for us to help when we are connecting for the polarity of these windings. So it's quite important, the polarity of these windings, with the direction of induced voltage, that we do that. If you've been setting up on transformers, you'll notice there's an X1 and an X2, and that coincides with that. It's the same principle, the polarity of it. So on this delta connection, we are going to get 3 different voltages. We're going to get voltage A to B, B to C, and voltage C back to A. So these are called line voltages, and in this case, it is the same as the phase voltage. So we have a whole module coming up on delta, and we are going to study this quite thoroughly, how these voltages come about, connecting loads to this, etc. So quite a bit coming up on that, figuring out current flow as well. The next connection, probably one of our most common, is the 3-phase Y connection or star connection. So also known as a 3-phase 4-wire. Very, very common. So in this case, what we see is that we have big A, which it could be X1, big B, X1 of the second transformer, big C, X1 of the third transformer. And then we'll have little a, little b, and little c, which is the X2 of each one of those single-phase transformers or ends of the 3-phase winding. And they're all connected together in the middle. And so we call that a star connection. That point in the middle is the point that we will ground. And we also take a wire off there, and that would be our neutral for a 3-phase system right here. So just like we saw in single phase, neutral is responsible for carrying unbalanced current, okay, and maintaining the equal voltages across loads that we connect between any one of the phases and neutral. So let's look at the voltages we have here. We have voltage produced A to B. We have a certain voltage there. We call that the line voltage. We have line voltage B to C. We have line voltage C back to A. And we also have 3 different phase voltages. Phase voltage VA to N, phase voltage B to N, and phase voltage C to N. So some typical, here's a typical voltage of a delta. So we've got 240 common, 480. Those are typical delta voltages. When we look at Y, and this is the similar configuration for 480 volt ungrounded system, we look at Y system, some typical voltage, you'll see ratings of 120, 208. That's a typical Y voltage. And when I see those 2 voltages, I know I'm dealing with a Y system. What's some other voltages you may see in a 3-phase 4-wire Y system? Well, 347, 600 volt, very common. Another one would be the 277, 480. You may run into that as well. So as soon as you see those 2 voltages like that, you know chances are you're dealing with a 3-phase Y or star system. Let's have a look here at phase sequence now. So back to the generator here. So when I have my crew generator here with my magnetic field on the outside, and so just a constant magnetic field going through, and I rotate this counterclockwise, if I follow what hits the North Pole, it would go A, the next one to hit would be B, and then the next one to hit would be C, and then we'd be back to A. So we'd have a standard phase rotation or a positive phase rotation, and we'd say it's ABC. That's so it goes A to B to C. We call that positive phase sequence. So if we look physically, VA to N would peak, then VB to N, then VC to N, and then we'd go back to where we started, VA to N on a Y system. So phase sequence for what do we got here? Positive phase sequence again. If we were to say, what is positive phase sequence? Well, we can say positive phase sequence would be A, B, C. So A peaks, then B peaks, then C would peak. Now, it doesn't really matter what letter of the alphabet we start with. If I started with B, C has to follow B, A has to follow C, and then B would have to follow A. So we just go back to the beginning. So all the way, these we can write it 3 different ways, and it's the same thing. It's A, B, then C. A, B, then C. A, B, then C, and back to A, right? So go C, back to A, then B. This is all ways to express positive phase sequence. So what would happen if I were to turn this generator in the opposite direction? We would get negative phase sequence. So negative phase sequence. Now we would get going clockwise. So if we started with C goes by, the next one to follow will be B. Then the next one to follow would be A, because we're going in the opposite direction now. So we got C, B, A. Or if I want to start the phase sequence with the letter B, it would be B, A, C. So if I want to start it with A, C, B. So let's just sub that in there. So once again, instead of it being ABC, like positive phase sequence, we now would say it's CBA. And so if I were to have this phase sequence, we call that negative phase sequence. Now, you can get a meter, a phase rotation meter, and you can connect it up to your red, black, and blue, and you can see which way it would go, it would turn. So you can tell whether your incoming supply is connected for a positive phase sequence or a negative phase sequence from the generator or from the secondary of the transformer. You can see what you've got coming in. Now, how do I change rotation on a 3-phase system? Pretty simple. Normal connection, we go A to T1, B to T2, C to T3, and all I got to do is swap or interchange any 2 of the leads. So in this drawing here, you see we've swapped T2 and T3, and now I've changed the order in which the motor receives the power. So on the top one, A, B, C, so turn this motor counterclockwise, and then if I swapped any 2, now I've changed the order so I can reverse the direction, and it's going the opposite direction now. So that's forward reversing starters, 3-phase. If you remember back how we did that, very similar, but we can quite easily change the direction of a 3-phase machine. So changing any 2 leads of the motor will change the direction and rotation of the motor. So what are some advantages of a 3-phase system? Well, it's got when we have a 3-phase motor, let's say, for example, we've got constant power. It's much smoother power with a lot less pulses or less pulsating. I got a little thing coming up. Next slide here. It's going to have a good graph of what we're talking about. The equipment can be manufactured much smaller. So if I were to say I had a 5 horsepower single phase motor versus a 5 horsepower 3-phase motor, that 5 horsepower single phase motor, to get 5 horsepower output of it, it's going to be a fairly large, heavy motor. And to do the same thing, we can make a much more smaller compact motor with 3-phase and still output the same 5 horsepower. Still do the same amount of work, right? So yeah. Now, the other thing with that is we don't really require any special starting for the most part on a 3-phase motor. With a lot of single-phase stuff, you'll have a start winding or a start capacitor, windings, extra windings that might come out of the circuit after it's running, and they're needed to get that motor going. With 3-phase, we don't need that. We can just apply voltage directly to the 3 windings, and it creates that rotational torque to get it going. So as a result, we can often have a lot less current draw as well going through this motor. Less current draw means less heat produced by the motor, less heat by the conductors, and because of that constant power, it makes it a lot more efficient as well. So let's have another look at that. So on the constant power, if we look at a single phase power, so we have our voltage. There's our voltage sine wave, and just assume it's true power, so current stays right in phase with the voltage. And power is E times I, so power equals E times I. If I were to multiply that out, Okay, so we'd have positive current times positive voltage. I would make one positive pulse and it would go all the way back down to 0. Now in the next cycle, current's in the negative, voltage is in the negative, and if I were to do all the instantaneous values, negative times a negative, negative times a negative, you'd see another positive pulse of power come down to the 0, and now they're both positive, positive voltage, positive current. But what we're really important here is that we go all the way up, come all the way down before the next one starts. So all the way up, all the way down. If we look at three-phase, okay, so there's our three voltages, and if we put our three currents in there, right in phase, that motor is always seeing three different pulses of power, and they overlap with each other. So that never goes without power. It just goes down a little bit, back up. Very small ripple here, right? That motor always has some form of energy that it's receiving and outputting at all times versus the single phase where it's got to go all the way up and down. And if we look at the time here, it's just very constant, smooth power with less pulses or less pulsating anyways. So that's one of the reasons why three-phase is so efficient and is desired, especially when we're getting into any larger motors. Okay, so next up, we're going to look at Y connections. We'll see you there.